I think this question you can find from YouTube also from Chambi and Himanshu Agarwal.
Okay.
So, so V out input they will give square wave with some 0 to 5 volt with the
Okay.
duty of 50%.
Okay.
So for one thing, that time, this is the time you can say, right? Time, or we can say this time period T.
Hmm.
So two cases will be there: time greater than tau of the circuit, and one case time
Okay.
is very less than that tau actually.
Got it. Got it. So what is your doubt?
Yeah, my doubt is here. I don't in these two. One case the output graph will be come like this, right? Somewhere like this, like this, like this, and it will stable here.
It is not visible to me. Yeah. Yeah. Fine. Yes.
Yeah, I think I don't remember which case. I think if t is greater than
Cannot you
tau,
think right now?
huh?
Cannot you think right now? Which case should be that?
Yeah, I am thinking that one. T is greater than tau. Yeah, I think this case t is less than tau.
E less than tau is the risk case. Okay. Fine.
Yeah, in this case, the output waveform will come like this actually.
Yes.
So it will reach to periodic steady state in DC here.
Okay.
So my question was, it will reach one DC value, right? Periodic.
Hmm.
So yeah, like this is my interview question. They asked why it is reaching to this value only exactly. Why not some other value? Means it is okay. It is growing, and suddenly stabilize at some point. So why it is stabilizing at this point only? Intuitively, they are asking to say without mathematical. I want to know this point. Actually, this.
That thing I can see because
Uh,
my input has some means what I can say. My input has some harmonics, like if I should say this input is growing from 0 to 5,
uh,
so it has some like my input can be represented as some VDC plus some harmonics or function of sinusoids with
hmm.
different frequencies like
Okay.
omega 2, omega naught, 3 omega naught, whatever,
Hmm.
or some DC. If I extracted out the DC, it will
Huh.
have some odd harmonics like omega naught, 3 omega naught, 5 omega naught, and so on.
Okay.
So we can see, depending on the cut-in frequency of the low-pass filter, which is 1 upon RC,
Huh.
after that it will block completely, and before that it will pass the frequency. So hopefully this DC plus some sinusoids are coming in the range of my low-pass filter.
Okay.
So these value it will give me at steady state. It should give me ideal steady state of DC value, but it
Huh.
is giving some ripple. The reason is that for the ripple, because some sinusoid frequencies are also coming in this range. So
Okay.
even around the DC value, it is trying to reach the DC value. Again, it is going little bit low. So such a ripples you can see.
Huh. Huh.
Not exactly. That is the reason. Because apart from this DC value, some sinusoids may come, and if no sinusoid is even there, then there is some DC value. And DC value is nothing but the average of this. When you
Okay.
convert into the when you will see its Fourier series transformation, you will
Okay.
see some DC component. On top of that, there are sinusoid harmonics are there.
Okay.
This can be the reason. It is
अच्छा
lending
अच्छा.
to some DC value.
Okay, okay. Because of low pass filter effect, input is combination of DC and some harmonics. So it is passing whole the
Hmm.
DC, which some harmonics are still
Yes.
coming. Because of this
Yes.
harmonics, ripple is coming.
Yes. Because whatever its value, even the cut-in frequency is very less, now it has to pass the DC. Because
Okay.
DC has no frequency now.
Yeah. Correct,
Let's
correct.
say inst instead of this, if my low pass filter is very sharp like this,
Huh.
then also it will pass my DC. Because DC is like nothing but comes on the F equal to 0.
Yes, correct, correct.
So it has to pass.
Hmm.
So this can be the reason.
Okay. Because of that one, it is achieving the
And
periodic steady
uh,
states with some ripples are coming.
yes. DC has to come.
Yeah, DC plus some ripple, like some AC.
Uh, some AC.
Yeah.
Yes. So if there is one more thing, if there is some rise in fall time now in
Yes,
my
yes.
input,
Huh.
like 0 to 5. This
Huh.
rise and fall times will give you some like bins of frequencies which are not the integral multiple. When
Okay.
I mean to say, when your input is like perfect square with zero rise and fall time,
Huh.
then you will get some harmonics like DC value plus omega naught, 3 omega naught, 5
Okay.
omega naught. When you convert into the Fourier transform, you will
Huh.
get the integral multiple of omega naught.
Okay.
But when my rise and fall times are exactly zero. But
Okay.
if there are finite rise and fall time, you will see some other frequency components also, not exactly integer, but omega naught you will see. Let's say zero point 0.1 omega naught you can see, zero point
Okay.
0.8 omega naught you can see. So any number you can see,
Okay.
depending on the rise and fall time. So
Yeah.
rise and fall time means not only the integral multiple of frequency.
Yeah.
Usually we see in the Fourier transformation that there are the integral multiple of fundamental frequency.
Yes, correct.
Usually this thing is only valid for when there is a perfect square with no rise and fall time.
Yeah.
So if there is some rise and fall time also associated with my input, this question can be asked in future. I am not sure because ideally people give a exact means without rise and fall time they give the input sinusoid. Oh sorry, square pulse or whatever they give a step input. They always give some step input with no rise and fall time.
Huh.
So in future this question can be asked. With the
Okay.
rise and fall time, you can have the different frequencies, not the
Hmm.
integral multiple. So many frequencies can be there. So
Yes,
in
correct.
that case, you will see if my
Hmm.
low pass filter is there. Uh, let's say my 3 omega naught was outside the band previously,
Hmm.
but because this is the case, zero point 0.1 omega naught can be there, zero point 0.5 omega naught can be there. So a lot of frequency components can come in the low pass filter range.
Yes.
So maybe apart from the DC, it can have lot of ripples.
Yes, correct.
This thing can you can see with FFT also.
Huh.
When you
Huh.
will do the FFT of this input, you will see
Hmm.
apart from the fundamental, which is like at centered at the F naught,
Yeah,
you
yeah.
will see lot of winds are there.
Some carrier frequency
Lot of
will
winds
come.
are there. So this is zero point 0.1 F naught, zero point 0.2 F naught. Lot of
Ah,
frequency will be
yeah.
there
Yes,
because of
correct.
finite rise and fall time.
Yeah. Hmm.
Hmm.
Okay, I think it's clear. It's clear, Anuj. I think I have one more last question. I will draw that
Hmm.
one. Can you try once?
Hmm. Hmm.
1 minute. Think this is somewhat very interesting. I am not able to solve. Means I didn't got the answer. That's why I'm asking you.
Okay.
This one, you know that career accelerator program is there, right? Whenever we joined,
Hmm.
that time Srikar, we and Srikar are
Okay.
that time this question Srikar asked to me.
Okay. Okay.
Yeah, that training time, someone asked, so I got this one. So
Okay.
I
Okay.
till now I didn't got answer. You can try once. So what they're asking was here, it is Vx. So they are saying, what is the value of Vx in
Hmm.
this case? I1 greater than I2. And what is the value of Vx in case of I1 less than I2? And they mentioned they are saying about this is the rail VDD and this is ground rail. Like in our chips also,
Hmm.
we will have rail, right? Two rails. One is positive rail,
Yes,
one is
yes, yes,
ground
yes.
rail.
Yeah,
Yeah,
yeah, yes, yes, yes.
yeah, they are saying this circuit is actually practical circuit. They taken from our your design only. I think maybe
Yes,
this
yes, it is
correct.
a practical circuit. It is a practical circuit. Yes.
Yeah, I think you know better than me. I think so. They are saying this is one rail, this is one rail. So now they are
Hmm.
asking Vx. What is the response of Vx in this case, this case? So can you brief me, explain here?
Actually, this question comes when we analyze this slew rate in system. Then
Okay.
also this question comes.
Yeah,
But I will not go in that depth. But yes, you can see the difference of current in the first case will flow inside the cap.
yeah,
So the cap will be charged.
yeah.
Okay.
Hmm.
So in that case, what? My difference current I1 minus I2
Hmm.
will charge the cap. Okay. So
Yeah.
it simply means when your I2 is less than the I1.
Hmm.
So it means what? this is the node where
Hmm.
my top current source is pumping more current.
Yeah.
It means, but you are taking less current out of it.
Okay.
So it means if you are pumping more current in a node, that node has to increase its voltage till the time it can reach the condition both the currents are same. Then
Yes.
only this node has some stable voltage such
Huh.
that we are pumping equal current, we are extracting equal current to the
Okay.
pumped
Yes.
current.
Yeah.
So means the difference current will go here and it will charge my cap such that this node will increase at some value so
Hmm.
that it is like pumping current equal to the current taking out.
Okay.
And the second case, when my I2 is higher, it means we are pulling some current, more current from the some node, and we
Hmm.
are only giving some lesser current to this node. It
Yes.
means some current will be supplied by this cap. So
Yes.
it's current supplied by the cap simply means this node has to go down such that again the pumped current equal to this current taking out. That's simple.
Yeah, and okay, what you were saying was here that I got your point. So here I1 and I2 are the current sources. So
Hmm.
Vx need to increase, but at what extent it will increase? 100, 200, infinite, greater than VDD or not? That's what the main question.
Huh? How it can be did?
Like if you continuously charge the capacitor, it will go more voltage,
Ah,
right?
that is no current. Yes, yes, it will go. It will go. Then it will go.
So then Vx will go more than VDD.
Yeah, yeah, it will go.
Vx.
The VDD is limit. Every system is limited by your supply voltage. Only in the case when what you are doing, your VDD has no effect on your current source. What is the ideal current source? Current source is what? Whether you are giving the VDD, this is my ideal current source.
Hmm.
Okay, what you are giving across it, it has no effect of this voltage.
Okay.
Whether I am connecting here my BDD, whether I am connecting here my ground, my current is not going to affect. That is the meaning of my ideal current source. What is the ideal current source?
Okay.
This is my V axis, this is my current axis,
Okay.
this is my I naught value. So my current is independent of the voltage. So whether it is a VDD or whatever it is, you're pumping an ideal current now. Then this node has to go away because there is a capacitor connected.
Hmm.
So it has no meaning with this node voltage because whatever difference comes across it, it don't has any effect. Because you can see simple this thing in RC circuits.
Hmm.
When we go some I naught we pump, we can put here VDD also. Simple like this is my capacitor, this is my resistor. So usually this question also comes into the RC question sections.
Hmm.
So whatever you connected here, it don't have any problem with it. You
Hmm.
can connect a VDD also, VDD or ground, whatever.
Okay.
Because you're pumping some constant current. You are considering that there is an ideal current which is pumping in this node, so the capacitor voltage will increase. No control on it.
Yeah, ideally it will go, but in practical scenario, I think it is not possible to go more than VDD, right? Like let's say rail to rail, like let's say that this current source also we can model as a MOSFET only, right?
Now, one thing is that, yes, I got your one point.
Hmm.
When you are saying the current source is ideal, you cannot stop it to increase beyond VDD.
Hmm.
But because in that case, my current has no dependence on the voltage.
Yes.
But if this is a practical current source, then what is this? It has some slope.
Yeah.
This slope is what? This is my V, this is my I naught
GM.
starting, and after this is I. So this is the dependence, means this is the voltage across this V is what? This V is nothing the voltage across my current source.
Yes.
So my current source has some dependence on the voltage. Then what will happen? Let's say this is my current source, this is my VDD, and if this is node my Vx, when my VDD reached equal to or my Vx reached equal to VDD, simply this has zero voltage. Sorry,
Yeah.
V current is equal to zero because this is the difference voltage and your
Huh.
Vx equal to VDD. Now it is zero. Now it is zero simply means if my I naught is a function of voltage across this, that
Okay.
I should say this V naught, and this V naught is zero, then my I naught has to stick on some value.
Huh.
Either it is a constant value or it is some value or it is zero value, whatever it is, it
Okay.
can be. So in that case, there may be some constant current, and if this node voltage reach there, so it depends on the circuit. More or like it depends on what the application there.
Okay.
Because this current source is not that ideal in the practical case. The first question was what? What the first question I have given?
Hmm.
This.
Yes.
What my PMOS was doing there? My PMOS was nothing but behaving as a current source only.
Yes, biasing only.
No, my PMOS, yeah, it was the only biasing circuit. I mean, it was only giving me the current.
Yes.
So practically, there is a current who is a dependency
Okay.
on like what voltage. You will
Okay.
see in this case, you will see for the PMOS if I'm using as a current source,
Hmm.
then this voltage has very significant importance. Like when my this let's say V out or Vx,
Hmm.
when my Vx minus VDD
Hmm.
is less than V overdrive value,
Okay.
my this reaching it is going out of the saturation, and it
Okay.
cannot act as a current source further. It is
Okay.
now not in the range of current source, so we cannot
Oh,
set current source after
yes.
that.
Hmm.
I think you got it.
Yes, correct.
Initially it
I
is in
got
this
it.
region, after that it is okay. So now you are in this region, now it is not a current source. In this region it is a current source.
Yes, yes.
So Vx has significance when it is a practical current source.
Yeah.
Hmm.
Yeah, that is up to my side. If you want, you can ask any questions. Otherwise, we
I
can end
think
up.
it is very I think long discussion for him. You remember and whatever the questions were there, try to recall for the Ramcharan I am saying.
Huh.
Try to recall and what best possible answer you can give. It will be very good for you.
Huh.
So tomorrow at what time your interview is there?
10 a.m. 10 a.m.
It's around 10 a.m. sir.
10 a.m. Okay, so take proper rest and just recall these questions. Or I think you can give half an hour here and half an hour in morning. Just go and give your interview with a very like you keep calm yourself and try to solve the things very carefully. Whatever he is asking, you can take your time properly and you can solve them.
Okay, sir.
Don't be in hurry. Don't do the mistake. Many of my friends did this mistake during the campus placement. They were trying to solve the question within a minute, but anyway they land up to the wrong solution. Then this is of no use.
Hmm.
So you can take the time. You can ask your interview, sir, I want to think like this. I have this approach. Please give me 2 minutes or 1 minute like that. I asked my interview two, three times because with a calm mind, with a cool mind, you can respond in the better way or best way, I can say.
Yes, sir.
Okay. So I think this is enough. Take proper rest because now 12 is already. So 10 a.m. means you have 10 hours total. So the rest is also proper, should be there like 7 hours minimum.
Okay, sir. Right.
Okay. I think Puneet, it is okay now.
Yeah, yeah, yes,
Tomorrow we'll
Sanuj.
meet in company.
Yeah, we will meet in office, bro.
Yes, yes, yes.
Yeah, you also take rest, man. Busy with US and Germany people.
From morning 7, night
What?
12.
Bro,
Continuous.
just tell to your
Okay.
manager,
Sir.
just tell to your manager, bro. Instead of this one, take me to Germany. I will handle. You can go and come in 1 week after 1 week.
uh,
Yeah, yeah. Ramchan,
okay.
you are saying something.
And
What?
sir, no, I was just I want to thank sir for making time for me.
What?
I would like to just thank you for making
Okay,
time
okay.
for me.
No, no problem, no
Uh,
problem. Okay. Actually, I like this thing. And Puneet told me yesterday also. So okay. Anyway, good. It's a nice experience for me as well. I learn a lot of things because whatever these circuits I told, I just like formed the circuits and after that analyzed along with you. So I learned these things. And during my design, I usually use these concepts, so that's why I can remember things also good, better way.
yes.
Okay,
Okay,
fine.
Anuj. Thank you. We will
Okay,
meet tomorrow
okay.
in office. We will discuss. I think
Yes,
so.
yes, yes.
Yeah,
Sure, sure.
yeah. Tomorrow I
Okay.
will message in WebEx. Okay, we will see.
Tomorrow also, I think entire day meeting for me. If I'll get time, I'll meet during the lunch for you like 10 minutes.
Yeah, fine, fine. Anything
And
is fine.
day after tomorrow, we can meet for a half an hour or 1 hour, no problem.
Ah, okay, bro. No, it's fine. We will meet day after tomorrow only, peacefully.
Yes, 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 yes,
Yeah.
yes. Okay,
Okay,
okay.
bro. Then good night.
Oh, okay, bye, good night.
Yeah, bye.
Yeah,
Bye, bye,
good
bye.
night, sir.
Bye, bye, good night.